Our next talk is by Guochao Sun, probing cosmic reionization with the tomographic ionized-carbon mapping experiment time. Thanks.
Okay, thank you. So, sorry, give me a second. Okay. All right, so hi everyone. I'm a rising fifth year graduate student at Caltech, and I'd like to first thank the organizers of SAZERAC for organizing the meeting and allowing me to give a live talk today. So today, on behalf of the TIME collaboration, I will talk about probing cosmic reionization with the tomographic ionized-carbon mapping experiment, or TIME. So just to get started, Kiri Kokare has introduced yesterday the idea of line intensity mapping from the perspective of millimeter wave instrumentation. But just in case some of you are still unfamiliar with this relatively new idea, I'd like to first quickly review the basic concept. So conceptually, intensity mapping refers to the statistical measurement of spatial fluctuations in the intensity of a certain emission without resolving individual emitters. So here is an illustration of basically what intensity mapping measures. So the two panels here compare the halo density field against the line intensity field, tracing the dark matter distribution in a sort of smeared manner. And because individual emitters are not resolved, intensity mapping provides an economical way to survey the large-scale structures in our universe with relatively coarse beams. And more importantly, intensity mapping is complementary to galaxy detection in the sense that instead of probing just the bright emitters, photons from even the faintest galaxies or diffuse emission can be captured in this case. And you are welcome to check out this review article by Eli Kovaz et al. For further details about the intensity mapping technique. Okay, so as we know that there are still a lot of open questions about the EOR and the cosmic dawn, and this is basically why we gather here today. And the answers to these questions can be actually studied by either resolving the sources, namely trying to detect individual galaxies and quasars, or by mapping the collective emission, line emission, as what people do with line intensity mapping technique. So as shown in this plot, the ionizing sources driving reionization can be studied by mapping tracers of star formation activities, such as H alpha, Lyman alpha, and C2, whereas the island of neutral IgM can be mapped by the 21 centimeter line of atomic hydrogen. And the complementarity between these tracers of ionized and neutral gas means that their cross-correlation can actually be used to confront foreground contamination, and more importantly, to constrain the reionization topology by tracing the size evolution of ionized bubbles. Okay, so there are a few reasons for C2 to become the target signal of our experiment time to study reionization. So first of all, the 158 micron C2 line is the major coolant of the neutral ISM, which makes it actually the brightest far infrared line that comprises up to 1% of the total far infrared luminosity of typical galaxies. Next, the C2 line has been identified as a reliable tracer of star formation with almost the same line luminosity versus SFR relation holding from local universe to redshift as high as 5 or 6. And also, as I've mentioned, that the cross-correlation of 21 centimeter signal between the 21 centimeter signal and C2 line in the near future will be able to measure the size evolution of ionized bubbles. And finally, the EOR C2 signal redshifts into a relatively transparent atmospheric window, which is important for ground-based observation like time. Okay, so just to give you some quick overview of the instrument and the kind of survey that we'll conduct. So the instrument of time is simply speaking a high throughput imaging spectrometer array consisting of two major components. So one is a total of 32 grating spectrometers that are divided into two banks, and one of which is shown here. And the other is the superconducting TES bolometers, which is why we need this multi-layer or multi-stage cryogenic system to cool the detectors all the way down to about 250 millikelvin for the detectors to work. And the instrument will be installed on a 12-meter ALMA prototype antenna at Kitt Peak. And here, the photo shows the moment when our cryostat was moved into the cabin of the 12-meter telescope during our first engineering run in the winter of 2019. And in terms of the survey strategy, as illustrated here, time is designed to conduct a 2D line scan to optimize the sensitivity and K-space coverage. And along the spatial direction, we will survey a total area covered by 180 by 1 beams. And along the spectral direction, we have 44 scientific channels covering a total bandwidth from 200 to 300 gigahertz. And each of those channels has a resolving power of about 100. All right, so in order to quantify how well time can inform us about reionization by mapping C2 emission, we need a valid model that links high redshift C2 emissivity to the reionization history. And specifically, our model is based on a simple linear relation between the C2 luminosity and UV luminosity of galaxies on log scale, which is calibrated against available observational constraints on the C2 luminosity function. And the UV luminosity, or effectively the star formation rate of galaxies as a function of halo mass and redshift, is then derived from the halo abundance matching technique. And the resulting star formation rate is used to calculate the global reionization history. So using our Fidesio C2 model, we expect time to measure the C2 power spectrum at a total SNR of greater than 5 in the two set bands of time. And it is important to point out that because of the nature of a line scan, C2 power spectrum that are originally measured by time will be in 2 dimensions, as shown by the black shaded regions, which are basically projections of the true 3D power spectrum showing red into the two-dimensional space by the survey window function. Okay, so from the power spectrum measurement, we expect time to, first of all, place some robust constraint on the C2 luminosity density between redshift from about 5 to 9, as shown here. And the cosmic star formation rate density can then be constrained to about 30% by marginalizing over the C2 parameters involved. And such a constraint from it is important to know that such a constraint from intensity mapping like time will not be dependent on assumptions of the about the faint end extrapolation. And then the most interesting application of time result to the EOR science is probably in terms of breaking the degeneracy between the average escape fraction of ionizing photons and the faint end slope of galaxy luminosity function. As you can see in this corner plot, the blue, red, and green contours represent the constraining power from just the CMB optical depth plus quasar absorption spectrum. And in the red case is the CMB plus quasar plus time. And finally, the green case is if we assume 2 times better time sensitivity. So the strong degeneracy between F escape and the faint end slope characterized by the parameter C may be lifted, especially after a factor of 2 increase of sensitivity is enabled by conducting a time-like survey from Chile. But of course, there is an important caveat here, which is that the C2 SFR relation must be known to very good accuracy to have such level of constraining power, which is in fact sort of difficult given the complexity of C2 production in the interstellar medium. All right, so just before finishing, I would like to spend a few more words about the issue of contamination due to foreground emission lines, as well as the opportunities they bring. So in practice, time will not only see the EOR C2 signal, but also pick up a series of CO rotational lines from lower redshift, as you can see in this plot. So these so-called line interlopers are mixed together with our target EOR signal and cause a serious problem of foreground contamination. And for example, in this plot, if you compare the C2 power spectral models showing blue and yellow to all the other lines representing the power due to like a CO foreground. But fortunately, to deal with these kind of like foreground emission lines, people have come up with a number of different techniques like I listed here, such as cross-correlation, masking, and the usage of K-space anisotropy. So that being said, these foreground lines are not just troublemakers. They actually provide useful probes of how the star formation is supplied by molecular gas near the so-called cosmic moon. Specifically, we are able to extract the strength of these CO lines by cross-correlating spectral channels of time corresponding to an adjacent pairs of CO transitions emitted from the same redshift. And then, as shown in this plot, if we assume some prior knowledge about the COJ letter, we'll be able to translate our cross-power measurement into competitive constraint on the cosmic molecular gas density. Okay, I guess just thanks everyone for listening. I'll just end up here with my summary slide and take your questions. Thank you.
Thanks very much. Just a quick question as the questions are coming in. You mentioned that your model was very dependent on knowing the C2 to SFR relation well. Have you thought about different far-infrared star formation traces to help you calibrate that relation, or looking to some of the other lines that you're open to detecting? Yes,
definitely. So I think since that in order to say anything about the EOR signs would require very good knowledge of, about like how we can convert like a C2 measurement into an SFR, we definitely want to consider in a like a multi-tracer context by including some other lines if they're available. They won't be available directly from our like time data set, but by combining with some ancillary data like say the observation of O3 or even some nitrogen lines, we're hoping to like use this like multi-tracer technique to help us better understand how we should convert our like C2 intensity into star formation rate estimation.
I think Renske Smith had a related point in that the O388 line is brighter than C2 for many of the redshift 8 EOR galaxies.
Exactly.
And easily detectable. And does that also help you to get rid of the interlopers, and would it be a better tracer than C2 to target?
Right, in some sense, yes. Like I think especially in the past few years, I think there are a lot of research about like O3 being like a brighter and even like more promising tracer of star formation rate in a very high redshift universe compared with C2. So I think definitely but like unfortunately time will not see it first of all, but I think a joint analysis or like will benefit a lot from the like recent studies of O3, like when we are investigating our like C2 observations.
Okay, I'll squeeze in one more question. How would your results change if the C2 SFR relation would break, i.e. change towards a steeper slope at low SFRs? That's a question from Yorick.
Right, so the C2 SFR relation, will mostly affect the shape of the power spectrum. So the exact slope and the intercept of this relation will have a strong effect on the exact shape of the C2 power spectrum that we see. So depending on the direction of changes, we'll probably have a lower or higher signal from our observation. But that also means that our power spectrum measurement will be like a sensitive tool to like help constrain the C2 SFR relation.
Okay, thanks very much, Jason. We'll move on to the final talk now, which is Yuichi Harikane. Would you be able to share your screen?